and it says that if it is a loopless graph G, you can always find a bipartite subgraph of that graph with at least EG by 2 edges. So EG is the number of edges in the graph G. Okay. So again I will state this to you. So suppose you are given any simple graph. Now it states that you can always find a bipartite subgraph of that graph G with at least mod E by 2 edges, where capital E is the, so you can say it like, anyways, EG is basically EG by 2 edges. EG is number of edges in the graph. So how this, so to prove it, they give a procedure to how to find out a bipartite subgraph for a given graph G. Suppose this is the graph. So since we know that in a bipartite subgraph, in any bipartite graph, what we have two partites, right? So it arbitrarily choose some partites. Say this is X, this is Y, and this is so Y. So vertex 1 is in partite Y, and 2, 3, 4, 5 is in vertex 2, 3, 4, 5 is in partite X. Okay. Now the algorithm goes like this: look for vertex V such that V has more neighbors in its own partite than neighbors in the other partite. Okay. You should look for those vertices V which has more neighbor in its own partite. वन को देख लेते हैं. वन के खुद के पार्टाइट में नेबर्स कम है, बट अक्रॉस द पार्टाइट नेबर्स ज्यादा है. So we don't need to bother about it. Say for example we take 2. 2 has two neighbors in its own partite, namely 3 and 5, and one neighbor in the other partite. So 2 is a candidate. So 2 is such a vertex V such that 2 has more neighbor in its own partite than the other partite. So what we will do, if this is the case, if it has more partite in its own, so we will shift it here. And we repeat this algorithm. Now we see that, look for 1. It has one partite in its own, one neighbor in its own partite, one neighbor in its across the partite. So we won't move it. 2 has one neighbor in its own partite and 2 neighbors across the partite. So 2 is not the right candidate. Now look for 4. It has more neighbors in its own partite than the neighbors in the other partite. So 4 is the right candidate to move. We will move it. Now at this stage you look into 4. Now you look into again 1. Okay, now you can look into 3. Say for example you look into 3. 3 has 2 neighbors in the other partite, 1 neighbors in its own partite. So 3 is not the right candidate. For 5, 2 neighbors in the other partite, 1 neighbors in its own partite. So 5 is not the right candidate. For 2, there are 2 neighbors across the partite. You cannot move it. 4, for 2 neighbors across the partite, you cannot move it. For 1, 2 neighbors in its own partite, but there is no neighbors in the other partite. So what we do, we will move 1 here. Okay. Now at this stage, if you look for all the vertices, you find that there is no vertex V for which V has more neighbors in its own partite than neighbors in the other partite. Check for 2. All its neighbor in the other partite. For 4, all its neighbor in the other partite. For 1, all its neighbor in the other partite. For 3, 2 neighbors in the other partite, 1 neighbor in its own partite. For 5, 2 neighbors in the other partite, 1 neighbor in the. So at this stage, the algorithm stops, and now it says that the bipartite subgraph is basically, now you look into this partite Y. If there is any edge within this partite, you remove that. Then you look into vertex X, you look, is there any edge within this partite? This edge is there, so you remove it. Now you get a bipartite graph. Okay, and you have to prove that. Okay, and you have to prove that it has so this was the graph, and if you remove this red edge, you will get a bipartite graph. Now we have to, so this is the algorithm through which we create a bipartite subgraph having more than EG by 2 edges. This is the algorithm. Now we have to prove that few things, that this indeed gives me mod E by 2 edges. So to prove it, the first thing that the natural question comes, there are 2 things we need to prove. The first thing we need to prove that this algorithm will stop after some time. It is not an infinite thing. Okay. The first thing we have to prove it is this algorithm will stop. So what is the logic behind it? Why this algorithm will stop? Now, say for example, initially I will again run the algorithm and tell you why the algorithm will stop. Okay. So initially this was my graph. Okay. And what I do, I look for vertex V such that V has more neighbors in its own partite and then the neighbors in the other partite. So at this stage, if you look into 1, it has more neighbors in the other partite, so no need to move. Now you need to notice that at each step of the algorithm, what we are actually gaining. That is something we need to look for to understand why the algorithm will stop after a finite amount of time. So now we have 2 edges across the partite. Now what we do, we move 2 to the other partite. The reason is it has more neighbors in its own partite rather than the other partite. So if I move 2 here, if I move 2 on the other side, what are the things that we have gained? The thing that we have gained is number of edges across the partite. Earlier it was 2 edges, now we have 3 edges. So across the partite, after each iteration of the algorithm, the number of edges across the partite keeps on increasing. Again, we move 4. So right now we have 3 edges across the partite, and 4 is the right candidate to move in the other partite. Now you see that we have 4 edges across the partite. So initially it was 2, in the next iteration it is 3, now it is 4. Now we find that 1 is the right candidate to move. In fact, 1 is the only candidate to move in the other partite because it has more neighbors in its own partite. So when I move it, we see that number of edges across the partite is 6. So from 2 it becomes 3, from 3 it became 4, from 4 it became 6, and at this stage the algorithm stops. Okay. So the algorithm is stopped. The reason is as follows. the number of edges across the partite keeps on increasing after every shift of vertices. Now, since the graph has finite number of edges, the strict increase is upper bounded by the number of edges of the graph. So this increase, this is a strict increase. So at every step, the number of edges across the partite increase strictly. And we know that since it is a finite graph, it has finite number of edges. So this increase cannot be cannot happen infinite number of times. So after a finite number of steps, we reach the maximum and we'll stop there. Now the question is, we have proven that the algorithm will stop, but we have to still prove that it has this across the partite, the number of edges is greater than equal to Eg by 2. That is something we need to prove. So the bipartite subgraph has Eg by 2 edges. That we need to prove. The algorithm terminates when all vertices V of the graph G has more neighbors across the partite than its own partite. Okay, so when the algorithm stops, every vertex has more neighbors in the other partite rather than its own partite. Now, suppose small dv denotes the degree of vertex V in the bipartite subgraph. जो bipartite subgraph मुझे मिला है एल्गोरिथम के बाद, उसमें हर एक वर्टेक्स का डिग्री है dv, and capital dv gives the degree of V in the original graph G. Now at termination of the algorithm, जब algorithm terminate हो गया, then for all vertex V, we know that dv greater than equal to capital dv by 2. Okay, why it is true? Because it says that number of edges across the partite is greater than equal to number of edges in its own partite. So this will happen at the termination of the algorithm. This will happen. Now we apply the degree sum formula. So if I do a summation on this, summation of dv is greater than equal to summation of dv. Now this summation of dv by 2 means, what is summation of dv? It is addition of all the vertex degrees, and we know that this summation of capital dv is basically 2 into eg. That is the degree sum formula. So 2 into eg by 2 is eg. So we have proven that at the end of the algorithm, what happens? This summation of dv, that means summation of all the vertex degrees of the bipartite subgraph is basically equal to eg. Okay. So what happens? If this is eg, then the bipartite subgraph has mod dv by 2 edges. So it is eg by 2 edges. Has at least, so has at least eg by 2 edges. That is how we prove it. So this is a very important theorem, and this is also a very interesting algorithm also. Now the next thing that we will prove is another interesting property. So okay, I will repeat this proof. I think some of you may have some confusion. I will repeat this proof. This termination is clear, right? Because at every step, the number of edges across the partite keeps on increasing, and we know that there are e edges. So this strict increase cannot happen infinite number of times. So after some time, it will stabilize. So after finite number of steps, the algorithm will stop. We have to prove that the bipartite subgraph is eg by 2 edges. So when the algorithm actually stops, then we know that for each vertex, it has more neighbors across the partite rather than its own partite. Now consider the dv, small dv is the degree of V in bipartite subgraph. And capital dv is basically degree of V in the original subgraph. Now at termination, we know that when terminated for all the vertex V, dv greater than equal to dv by 2. तभी terminate होगा. Otherwise the algorithm won't terminate. Okay. Now अभी degree sum formula मैं यहाँ पे apply कर रहा हूँ. Summation मैं दो side में use कर रहा हूँ. So what happens? This summation of capital dv by 2 is summation of dv is basically 2 into eg. So 2 cancels out, So summation of dB is Eg. So bipartite subgraph में, so what this means, the bipartite subgraph में degree sum है Eg. अगर bipartite subgraph में degree sum है Eg, तो bipartite subgraph में कितने edge रहेंगे? That is, from degree sum formula we know that if it is summation dB by 2, so there will be Eg by 2, at least Eg by 2 edges. Okay. So this is the proof. Next we will go to another interesting theorem. So okay, I'm just coming back. You just read it. Okay. So the maximum number of edges, this is Mantel's theorem. Okay, the maximum number of edges in an n vertex triangle free simple graph is floor of n square by 4. Okay. So it's a the statement I will again repeat. So you are given a simple graph of having n vertices. Okay, and the special property is the graph is triangle free. Now we have to prove the maximum number of edges. Sorry, the maximum number of edges in such a graph is floor of n square by 4. Okay. So first part, so it's a very interesting proof. So what we do, suppose the graph has n vertices v1 through vn. Okay. Now among them you choose that vertex u having maximum degree, जिसका डिग्री सबसे ज्यादा है. Now it may so happen के there are multiple candidates, or I should say there are multiple vertices having the same maximum degree. Okay, so in that case you choose any one of them. Okay, so choose the vertex u, or I should say choose any vertex u, choose a vertex u having maximum degree, and suppose this maximum degree is k. So delta G represents the maximum degree of a vertex, so that is equal to k, and small delta G represents the minimum degree of a vertex of a graph. Okay. So suppose you having the maximum degree, okay, and that is k. Now what we do? We try to draw this graph. So this is my u having the maximum degree. So there are k edges here. Okay. Now this set is basically the set of vertices which are neighbors of u. That is why x equal to nu. That is, x is the set of vertices which are neighbors of u, and all other vertices are in this partite y. Okay, so y में कौन सा vertex रहेगा? Capital V is the total number of vertices minus u and minus the neighbors of u. Okay, so that is how we create this graph. Okay, so I will again repeat up to this. Sorry. So we have n vertices, out of which we choose that vertex having the maximum degree. If we have more than one vertex having maximum degree, then we choose any one of them. Suppose u is a vertex having maximum degree, and this maximum degree is k. Now we'll create this graph. U is keeping we keep u separate. All its neighbors are in some partite, and rest of the vertices in the other partite. Now, few observations. The question is, can there be any edges here? In this graph, can there be any edges within X? The answer is no. Why? Because if there is any edge here, it will create a triangle. Right? If there is any edge here, it will create a triangle. If there is any edge here, from this to this, then it will create a triangle. Now we know that this is a triangle-free simple graph. Okay. Since the graph is triangle-free, no edge exists in X. So there is no edge in this partite. Okay. That is the first thing that we need to understand. Now, every edge, ये ग्राफ में जितने भी एज है, has at least one end point in V minus NU. यहाँ पे जितने भी इस ग्राफ में जितने भी एज है, सबका एक कैरेक्टरिस्टिक्स में देखना चाहता हूँ, एक प्रॉपर्टी देखना चाहता हूँ. एवरी एज इन दिस ग्राफ हैज वन एंड पॉइंट इन V माइनस NU. ठीक है, एग्जांपल ले लेते हैं. सपोज इस एज को मैं ले लेता हूं. इस एज का एक एंड पॉइंट तो NU में है, पर दूसरा एंड पॉइंट इज U itself. Okay, so that means again V minus NU. So V minus NU means this is the vertex U and this total partite Y. U and this total partite Y. So every edge has at least one point in mod in. So every edge has at least one point which is maybe U or maybe some vertex in the partite Y. So for these edges we know that one end point is NU. For this kind of edges which is across X and Y, one end point is in Y, and there may be some edges which is within Y. So both of the end points belongs here. So that is why like every edge has at least one end point in this. It may so happen the edge has both endpoints in Y. That is also possible for this edge. Okay. Now, if that is the case, so based on these two observations, we can say that what is the number of edges? So हम लोग डिग्री सम फॉर्मूला में जो पढ़े थे वो ये था कि summation of degrees by 2 is equal to number of edges. So since every edge has at least one point in V minus NU, so number of edges is less than equal to K. So K coming from for this K edges which are neighbors of U, K plus how many vertices are there in this Y. So if there are total n vertices in the graph, out of which K vertices are there in X and one vertex is this U. So the mod Y, basically mod Y is nothing but number of vertices in Y, and which is nothing but n minus K minus 1. Okay. So now if we, since every vertex, each of these vertex has, so since the graph has maximum degree K, तो ये सब वर्टेक्स का मैक्सिमम डिग्री क्या हो सकता था? K ही हो सकता था. So n minus K minus 1 into K. So that is the maximum number of edges that is possible in this graph. Okay. So for U we count K. For so how many vertices are there in partite Y? That is n minus K minus 1. So, and for each of these vertices, the maximum degree could be K, because we know that delta G is K. Now, if we sum them up, it turns out to be n minus K into K. So so number of edges in the graph, in the n vertex triangle free simple graph, follows this equation, follows this inequality. E less than equal to n minus K into K. Now n minus K into K is maximized. So our objective is to find the maximum number of edges. So when n minus K into K will be maximized? When K equal to n by 2, if n is even, right? that we can found out from our calculus course. So n minus k into k is maximized when k equal to n by 2, if n is even. Now you put k equal to n by 2, so n minus n by 2 is n by 2 multiplied by n by 2, so e less than equal to n square by 4. Now what about if n is odd? If n is odd, then n minus k is maximized when k equal to n minus 1 by 2. Okay, so you put k, the value of k as n minus 1 by 2, so it turns out to be n square minus 1 by 4. Okay, in both of the cases, either you take n square by 4 or n square minus 1 by 4, it is nothing but floor n square by 4. Okay, so that is how we prove this Mantel's theorem, that if you are given an n vertex triangle free simple graph, then the maximum number of edges is floor of n square by 4. Now the question is what Mantel has proven. This is an upper bound, right? E less than equal to n square by 4 when n is even, e less than equal to n square minus 1 by 4 when n is odd. The question is it a tight bound? So is it a tight bound? The meaning of tight bound is, can we really construct a triangle free simple graph of n vertices, where in one case n is odd, in another case n is even, where e actually equals to n square by 4. We know that e less than equal to n square by 4. So if my question is, if n is even, can I construct a simple n vertex graph whose number of edges is n square by 4, or if n is odd, it is n square minus 1 by 2. So e equal to n square by 4 when n is even, ऐसा ग्राफ हो सकता है क्या? Yeah, if n is odd, whether we can get a graph where number of edges is actually equal to n square minus 1 by 4? The answer is yes. So in the next slide we will see these graphs. So both are bipartite graphs. So Mandel's theorem का tight bound है. So यहाँ पे देखो number of vertices is odd, 5. So 5 square minus 1 by 4, that means 6, right? 5 square minus 1 by 4, that is 6. So it has 6 edges. It is a complete bipartite graph. Similarly, if n is even, this is n square by 4. So n is 6 here. So 6 square by 4, that is 9. 36 by 4, that is 9. So there are 9 edges in this graph. So it is not only it's an upper bound, it is also a tight bound also. So that tight bound is achieved when we get a bipartite graph, and we know that bipartite graph is a triangle free graph. Why it is a triangle free graph? Because bipartite graph, we know that bipartite graph की एक property है, it doesn't have an odd cycle. So if it is a triangle, it is an odd cycle, right? So this is a very good theorem. It's a nice theorem, which basically you can see that it can characterize as a bipartite graph also. Basically, it characterizes not only bipartite graph, I should say it characterizes any triangle free graph. Even if the graph has a pentagon also, it has an odd cycle. But in that case also, we know that the maximum number of edges is floor of n square by 4. Okay. So, okay. Next we go to a definition which is called degree sequence. Okay. So degree sequence simple graph के लिए भी defined है, non simple graph के लिए भी defined है. So first we'll so जब simple graph के लिए हम degree sequence बोलते हैं, उसको हम लोग graphic sequence बोलते हैं. So we'll look into all these things. So the degree sequence, so the degree sequence of a graph is a list of vertex degrees, usually written in non-increasing order as d1 through dn. So basically what happens, suppose you are given an n vertex graph. Suppose this is a 4 vertex graph. तो इसका डिग्री कितना है? 3 वर्टेक्स 3 का डिग्री है 4. ओके, बिकॉज लूप विल काउंट ट्वाइस, राइट. इसका डिग्री है 4, इसका 4 का डिग्री है 3, 2 का डिग्री है 3, 1 का डिग्री है 2. सो हाउ डू वी राइट इट्स डिग्री सीक्वेंस? फ्रॉम लार्जेस्ट एलिमेंट टू स्मॉलेस्ट एलिमेंट. सो 4 3 3 2. So 4 3 3 2. Okay. So that is how we write the degree sequence of this graph. So given this graph, if somebody gives you this graph and asks you to what is the degree sequence, so you should say that it should be 4 3 3 2. So basically you have to list down all the vertex degree in decreasing order, more specifically in non-increasing order. Now we have to prove something. For a so degree sequence, when we talk about degree sequence, you should keep in mind that degree sequence talks about non-simple graph. So the graph may have edges, the graph may have parallel edges, the graph may have self loops also. Theorem is the non-negative, so it may be 0 or positive, right? The non-negative integer d1 through dn are the vertex degrees of some graph if and only if mod di is even. Okay, so only if part हम लोग पहले प्रूफ कर लेते हैं. only if पे हम लोग what is given to us, given is you are given n different non-negative integers d1 through dn which are basically vertex degree of some graph. So basically you are given 4 3 3 2 and they ask you to prove that the summation of them must be even. Now it is since we already know that summation of all the vertex degrees is basically equal to 2 into eg, which we know from the degree sum formula, and 2 into eg must be an even number. So this direction is very easy. From degree sum, directly applying degree sum formula, we can figure it out that summation of di equal to 2 eg and which is even. Now we have to prove the if part. So if part is, suppose somebody tells you you are given few integers d1 through dn and such that summation of di is even. So summation di of is even. Then you have to tell that, then you have to prove that this d1 through dn, these numbers basically correspond to some vertex degrees of a graph. I will repeat this statement. So first thing we have proven that you are given this graph. Since this graph is given to you, you know what are its vertex degrees, and you say that summation of this is even. That is something you have to prove. Next thing what they have done, they will give you these numbers d1 through dn such that summation of di is even. Now your task is to construct a graph. Your task is to construct a graph which satisfy this property. That means each vertex, so there are n vertices and each vertices has degree d1 through dn. Now from 4 3 3 2, you may create this graph, but you may not create this graph also. So but your task is to given like this. Okay, so you are given this 4 3 3 2 such that you see that the summation 4 plus 3 plus 3 plus 2, that is 12, which is an even number. Now they ask you to construct a graph having 4 vertices where one vertex has degree 4, another vertex has degree 3, third vertex has degree 3 and fourth vertex has degree 2. So what do you do? So since there are 4 vertices, you draw them 1 2 3 and 4. Suppose so the first one is correspond to vertex 1, this is vertex 2, this is vertex 3, this is vertex 4. Now we also know from the property of a graph that number of odd degrees in a graph is even. So यहाँ पे 2 3 वैल्यू है, right? The 3 appears twice. So number of odd numbers in this list must be even. That we know from the property of a graph. So this first one corresponds to vertex 1, this second one corresponds to vertex 2, this third one corresponds to vertex 3, and fourth one corresponds to vertex 4. So for vertex 2 and 3, we see that they are odd. So what I do, between 2 and 3, we put an edge. Now if we put an edge, the degree sequence like 4, 2, 2, 2, right? Since I put an edge, it converts to this degree sequence where all of them are even. Now what we will do, so vertex 1 has degree 4. So vertex 1 में मैं 2 सेल्फ लूप लगा देता हूं. वर्टेक्स 2 का डिग्री है 2, यहाँ पे एक सेल्फ लूप लगा देता हूँ. वर्टेक्स 3 का भी डिग्री है 2, इसमें एक सेल्फ लूप लगा देता हूँ. वर्टेक्स 4 का भी डिग्री है 2, तो एक सेल्फ लूप में लगा देता हूँ. नाउ दिस इज ए ग्राफ. Now this is a non-simple graph, right? So basically, 4332 say you cannot construct this, but you can construct a graph which says that if when summation of the when degree sum formula is even for a set of integers, then you can always construct a non-simple graph like this. Okay, so that is how the on leaf. So इसका written statement यहाँ पे है. यही जो है ये बुक स्टेटमेंट ऐसा है. Same theorem. Suppose d summation of d is even, then we construct a graph with vertex v1 through vn and dvi equal to d for all i. Since summation of di is even, the number of odd values is even. First, form an arbitrary pairing of the vertices such that, so odd vertices को मैं pair up करूंगा with edges. For each resulting pair, form an edge having those two vertices as endpoints. So odd vertices को मैं pair up करूंगा, and the remaining degree needed at each vertex is even, and they must be non-negative. So to satisfy this, we place floor di by 2 loops at vi. So this is the statement that is written in the book, but what I show that how it is actually being done. Okay, so this is something I have written in my own words. So that is the statement of the, so if part, so only part के लिए तो यही है book के statement. If part के लिए जो मैं यहाँ पे pictorially आपको describe किया, that is written out here. So basically I will again repeat, since the summation of degrees is even, we know that if there are odd numbers, number of odd numbers will be even here. Okay, so we will pair up these odd combinations and we'll place edges between them. So this is vertex 2 and this is vertex 3. So 2 3 के बीच में मैं एक edge डाल दिया, and if I see what is the, so how the degree sequence change, 4 2 2 2. So everything is even right now. When everything is even, then very easy. If this is 4, we will put 4 by 2 loops in vertex 1, that is 2 loops in vertex 1. This is 2, so 2 by 2, that is 1 loops in vertex 2, 3 and 4. So this is the degree sequence of non-simple graph. Okay. Then, okay, you take a break for 5 minutes. Then we'll discuss what is the degree sequence of simple graph and we will prove some properties. Okay. So take a break for 5 minutes, then we'll again come back. Okay, let's begin. So far we have studied degree sequence of non-simple graph, and also we have proven a theorem where it is said that if you are given some non-negative integer d1 through dn, which are basically vertex degrees of some graph, then it is possible if and only if di is even. Okay, so we have proved like this. If you are given a graph, then we show that its degree summation is even. And again, if the graph is not given but the degrees are given and it says that summation of di is even, then we can always construct a non-simple graph from it. Now, degree sequence is defined for a non-simple graph, but if it is a simple graph, it gives a special name that is called graphic sequence. So graphic sequence, when we talk the graphic sequence immediately means we are talking about a simple graph. The graphic sequence is a list of non-negative integers, that is the degree sequence of some simple graph. So degree sequence of simple graph is called the graphic sequence. Okay. So a simple graph with degree sequence d, a simple graph with the degree sequence d realizes d. Okay, so this is a kind of thing that is being written now. This realization. So basically, out of this, the important thing you have to know that अगर degree sequence मैं बताता हूँ तो it may be a non-simple graph, it may be a simple graph. But if I say it is a graphic sequence, that means it is a degree sequence for some simple graph. So degree sequence. So ये मैं थोड़ा सा highlight कर दूँ, degree sequence of some simple graph. Bold. Now we will prove Havel and Hakimi theorem. Havel and Hakimi proposed a characteristics. What they told that if the graph has more than one vertices, okay, for n greater than 1, an integer list d of size n is graphic if and only if d prime is graphic. What is d prime? D prime is nothing but it is obtained from d by deleting its largest element delta and subtracting 1 from its next largest elements. The only one element graphic sequence is d1 equal to 0. Okay. So first we try to understand what Havel-Hakimi's theorem statement means. Okay. First we consider the last statement. The only one element graphic sequence is d1 equal to 0. So ये कब होगा? Suppose the graph has a single vertex. So it is a simple graph. It is a simple graph. It doesn't have an edge, because if it has an edge, it must be a self loop, and if it is a self loop, it cannot be a simple graph. So if a simple graph has a single vertex, it cannot have any edge. It cannot have any edge, right? That is why d1 equal to 0. So one vertex simple graph ke liye we prove that it is 0. So the only one element graphic sequence is d1 equal to 0, and which basically corresponds to a simple graph having a single vertex, and definitely the graph cannot have any edge. This is the trivial statement. Okay. Now for n greater than 1, if the number of vertices is greater than 1, then what is the characterization they made? So what they say, okay, an integer is d. So d is a graphic sequence if d prime is graphic sequence, where d prime is obtained by deleting the first element, the largest element delta from it, and subtract 1 from the next largest element. So basically what it says, K 3 2 2 1, this is a graphic sequence. Why it is a graphic sequence? So what they say is, Havel-Hakimi theorem says that if I delete 3 and I delete 1 from next 3 elements. So if I delete 3 and I delete 1 from 2, so it became 1. I delete 1 from 2, so I subtract 1 from 2, so it is 1, and I subtract 1 from 1, so it is 0. Now I delete the largest element, that is 1, and I subtract 1 from the next 1 element, so it became 0, 0. Now 0, 0 is a valid graphic sequence. Why? Because it represents 2 vertices and there is no edges between them. So it is a disconnected graph of 2 vertices. So it is a valid graphic sequence. Again 5, 4, 2 and 1. So that is another valid, that is also a graphic sequence. Why? If we delete 5 and you subtract 1 from next 5 elements. So here 2 becomes 1, this 2 becomes 1, this 2 becomes 1, and last one is 0. Now you remove this one. If you remove this one and you subtract 1 from the next one, so you remove it and 1 becomes 0. So 0, 1, 1, 0. Now we know that the sequence should be put in an increasing order, sorry, in a decreasing order. So we put, so 0, 1, 1, 0 can be written as 1, 1, 0, 0. Okay. That is from the definition. Now again I get the maximum one, that is 1. I remove it and I subtract 1 from here, so it is 0, 0. Now 0, 0 is again a valid graphic sequence. It corresponds to 3 vertices and which don't have any edges between them. Okay. But 4, 3, 2, 1 is not a valid graphic sequence, because if I delete 4, I need to have 4 elements next, from which I must delete 1. So it became 2, it became 1, it became 0, but I do not have a third sequence here. So this is not possible. Okay. If I delete 4, I need to delete 1 from next 4 elements, but this next 4 elements doesn't exist at all. So if I put it 1, 1 like that, then what will happen? Let's see. So it will be 2, 1, 0, 0 in that case. Okay. Now if I delete 2, if we delete 2, then this 1 became 0, next 0 will be -1 and then 0. But negative number cannot come, so it is not a valid graphic sequence. So 4, 3, 2, 1, 1. Okay, it is not only that, so it's like let's put it like this. Then what will happen? If I delete 4 and then it became 2, it became 1, it became 1, it became 0. So now it is a valid graphic sequence. Okay, so it is again, because if I delete 2, then it becomes 0, 0, 0. Again, it is a valid graphic sequence. So what they are trying to say, okay, if this is a simple graph, so now we have to prove this statement. What we have to prove? For n greater than 1, for n equal to 0, sorry, for n equal to 1, we have already proven that. Because for n equal to 1, we know d1 must be 0 and it is, the simple graph looks like this. So that is done. This proof is a trivial proof. This is a trivial proof. We have to prove this one for n greater than 1 and integral is d of size n is graphic. If and only if d prime is graphic, where d prime is obtained from d by deleting its largest element delta and subtracting 1 from its next delta, next largest element. Now the thing is, now what is a graphic sequence? Graphic sequence is a degree sequence of some simple graph. Okay. So, okay. If part we need to prove. What is if part? If part says that in if part, for n equal to 1, the statement is trivial. We have already proven that. For n greater than 1, what is given to us and what we have to prove. So we are given D. What is D? D is a sequence of n integers. Okay. And we are also given a simple graph G prime with degree sequence D prime. Okay. So these two things are given. So we are given D and we are given D prime along with a simple graph G prime. Now our objective is to prove that D is a graphic sequence. So to prove it, what we will do, we will create another simple graph G from G prime which realizes D. I will again repeat this statement. So what is given to us? We are given this n integers and also we are given a simple graph G prime with degree sequence D prime. And how D prime is got? So D prime is got by deleting the largest element from D, and for next n integers we will subtract 1. Okay. So we take an example and we try to understand how we will prove it. So suppose this is given to me. This is D. D1, D2, D3, D4. Along with that, we given a simple graph G prime 2, 1, 1. Suppose Y has a degree 2, Z has degree 1, X has degree 1. Okay. Now, so if I delete 2 from here, this will be 1, this will be 1, and this will be 2. So it is my D2 minus 1, this is my D3 minus 1, and this is my D4. Okay. Now what I do, they ask me, okay, this is also graphic. That means we need to create a simple graph corresponding to this D. So what should we do? Since a single vertex is deleted, so I will create another vertex W here, and I make W adjacent to those vertices which have value D2 minus 1 and D3 minus 1. So from here I got this, then I create W and I make D2 minus 1 and D3 minus 1, that is 1, 1 adjacent to W, and I create this graph. So this is a simple graph. So the proof statement is we add a new vertex W adjacent to vertices in G prime having degrees D2 minus 1 to D delta plus 1 minus 1. These Di are the delta largest elements of D after delta itself. So, but D2 minus 1 and this one need not to be this largest number of this. So, this is not important. Basic important part is how do you create this graph? So, you are given this. So, your input is this graph and this. So, from here you know that you delete 2, it results in 1, 1 and 2. Now, you will find in this graph which vertex has degree 1 and 1. So X and Z are those two vertices. So you create another vertex and you make that vertex W adjacent to X and adjacent to Z. And that is how you create a graph which realizes D. Okay, so this if part is easy. The difficult part is this. Suppose you are given a simple graph G with degree sequence D. Okay. Now they ask, now your task is to produce a simple graph G prime with degree sequence D prime. That is something you have to do. Then things will be done. So suppose this is the graph. So let W be the vertex of degree delta. सो इस ग्राफ में अगर देखोगे तो द डिग्री सीक्वेंस इज 33332. So suppose so highest degree is some vertex having degree 3. Suppose this is that vertex. Okay. So let W be the vertex of degree delta in G. Let S be a set of sigma vertices. S be a set of delta vertices in G having the desired degree D2 to D delta plus 1. If NW equal to S, then we delete W and we will get G prime. Okay. So what it tells, so there are two things will happen. Two things can happen. Basically, you are given a graph G with degree sequence D. Now your task is to produce a simple graph G prime with degree sequence D prime. So what you will do first, suppose this graph is given to us, whose degree sequence is 3332. Now what you do, you choose any vertex having degree 3. Okay. Suppose you choose this one. Okay. And what you do, you delete it. If you delete 3, these 3 edges will also be deleted. So it turns out to be this graph. Okay. Now if you delete 3 from here, so this will be, if you delete 3 from here, it will be 2, 2, 2 and 2. Okay. And you get the same graph having edge. So each vertex, if you delete 3, if you get this graph, where each vertex is of degree 2. So what happens? We are done. Why it is so? You read this statement. Let S be a set of delta vertices. So here delta is 3. S be a set of 3 vertices in G having the desired degree D2. So my D1 is 3. My D1 is 3. Having D2, D3, D4. Okay, because this is 3. So D2, D3, D4. If neighbor of W is equal to S, then we can delete W to obtain G prime. So अगर मैं अगर given this graph and given this degree sequence, if I choose the right vertex, then what happens? Okay, I will get we can easily produce a G prime with degree sequence D prime. So what is input to me? To me the input is this graph, this D and this D prime. These 3 things are input. Now I choose randomly any vertex W having degree 3 and I delete it. And if I get a graph like this which corresponds to D prime, then I am done. Okay. And when this is happening, it is not always happening. In this case, it is happening. We will see some cases where it is not happening. So it is only happening if S be with respect to this graph I am explaining. Here delta is 3. So W be a vertex of degree 3 in G. Let S be a set of 3 vertices in G having the desired degrees. D2, that is 3, 3 and 3. D2, D3 and D4. In that case, if neighbor of W is equal to S, so ये जो next 3 जो vertices हैं, ये 3 अगर इस first vertex का neighbor है, in that case we can easily produce G prime by removing this one. So this is the simplest case where we choose the right vertex. Now what will happen? Let W, तो ये सेम ग्राफ पे मैं दिखा रहा हूं 33332. ओके सॉरी, ये सेम ग्राफ के लिए अगर मैं ये W इसको चूज करता, इसके जगह इसको मैं चूज करता, तो व्हाट प्रॉब्लम विल हैपन? लेट W बी द वर्टेक्स ऑफ डिग्री 3 in G. Suppose I choose W this. Okay. Now let S be a set of delta vertices in G having the desired degrees d2 to d3. So basically let S be the three vertices, here delta is three vertices in G having the desired degrees 3, 3 and 3. So d2, d3 and d4. Delta is 3, so d2, d3 and d4. So what is my S? If I choose this my W, then S is 3, 5 and 4. Okay. 3, 5 and 4 because they also have degree 3. But now you see that in the earlier case, NW, neighbor of W equal to S. Here in this case, neighbor of W doesn't not equal to S. Because 3 is a neighbor of 2, 5 is a neighbor of 2, but 4 is not a neighbor of 2. 4 is not a neighbor of 2. So if NW not equal to S, then what will happen? So if NW equal to S, we are done. If NW equal to S, then we delete W to get G prime. जैसे इस केस में हुआ था. But we do not know that which vertex to choose as W. Suppose I choose this vertex as W, then what will happen? So if neighbor of W is not equal to S, so my neighbor of W is 3, 5 and 1. Okay. My neighbor of W is 3, 5 and 1 and my S is 3, 4, 5. Because vertex 3, vertex 4, vertex 3, vertex 4, vertex 5 has degree 3. So that is my S. But my neighbor of W is not equal to S. My neighbor of W is 1, 3 and 5. Okay. So so my task is, how do I modify my graph G to increase? So what is NW intersection S? So NW intersection S is 3, 5. Okay. And mod of that is means there are two elements, so 2 and 2 not equal to 3. So objective is to make NW intersection S equal to 3 such that it respects D prime. So I have to change this graph in such a way, I have to increase the degree of W in such a way. So I should change the graph, I should modify the graph in such a way that NW intersection S, which is right now 2, should increase to 3 and it will respect G prime. Okay. So how do we do this? To do this, what they say is that choose. So what is S? S is those vertices having the desired degrees d2, d3 and d4. So these vertex 3, vertex 4 and vertex 5 have desired degree. And NW is actual neighbor of W, that is 1, 3 and 5. So choose a vertex X belongs to S and a vertex Z which doesn't belong to S such that W is not adjacent to X and W is adjacent to Z. Okay, ये लाइन को हम लोग देखेंगे. So in this graph, what is my S? S is 3, vertex 3, vertex 4 and vertex 5. Now out of this, I have to choose some vertex as my X such that this X is not adjacent to W. That is 4 is X here. 4 has degree 3, but 4 is not adjacent to W. Okay. And also we have to choose a Z which doesn't belong to S. So 3, 4, 5 may doesn't belong to S means 1. The vertex 1 which is adjacent to W, but it doesn't belong to S. Okay. So basically this is my Z. Z is 1 and X is 4. Now what we want to add? We want to add WX and we want to delete WZ to maintain degree of W equal to 3. While preserving the vertex degree. Okay. So what we do for this graph, okay. Now, so basically choose x which is belongs to S. So this is my x which belongs to S and which is not a neighbor of W. Okay. Also we have to choose a Z which is a neighbor of W, but this Z is not a part of S. Okay. So this is my x, this is my Z with respect to this picture. Now my objective is we want to add this Wx. We have to create an edge here and we want to delete this edge from here to maintain degree of W as 3 while preserving the vertex degrees. Now, what are the challenges to do that? Since degree of x, this is the degree of x, is greater than degree of z. Why? Why degree of x will be greater than degree of z? Because we know that due to our choice of S. What is S? S is the next three neighbors of W. S is the, so this is my W, the next three neighbors is 3, 4 and 5. Why we choose 1? Because it has less degree. Since degree of x is greater than equal to degree of z, and already W is a neighbor of z, but not x. W is a neighbor of z, but not x. There must be a vertex y adjacent to x. There must be a vertex y adjacent to x, and which is not adjacent to z. So basically what it is trying to say that W neighbor has z which is not belongs to S. Then S में एक vertex है 4 which is not a neighbor of W. Now our objective is to add the edge to 4 and delete the edge to 1. Now to do that, what we do, we know that since degree of x is 3 and it is greater than dz, so, and already W is a neighbor of z. So this x has a neighbor y which is not a neighbor of z. So what we do, we add 2 4, we add 2 4, we delete 2 1, we delete 2 1, and we add 1 5, and we add 1 5. As a result, so this, what this transformation will give, this transformation will increase, will keep the vertex degrees intact. So now this vertex has degree 3, 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 this vertex has degree 2. So it creates a new graph G star which has which respects this D, which respects this degree sequence. Now if I delete W, you see that in this case NW equal to S. So NW, NW equal to S. That's why NW intersection S is 3. So algorithm stops. So now I can delete this W and I create this graph. So I can realize this 2 2 2 2 with this new graph, and it is a simple graph. Okay. So and the formal way it is proving is written here. So again it is an algorithmic proof. So basically what we do here, You are given a graph. In the only part, you are given a graph having some degree sequence d, and you are given a degree sequence d prime. Now your task is to create a simple graph which realizes d prime. अभी d prime, so इस ग्राफ से मुझे कोई एक वर्टेक्स हटाना पड़ेगा such that respects my d prime. Now I do not know which vertex to use because there are multiple vertex having the same degree. तो अगर मैं इसको हटा देता, अगर मैं इस 3 को हटा देता, I will get nw equal to s and I am done. So if I delete this, I find that the 5 to 1 for this graph is having the degree sequence 2 to 2 2 and it matches. So I am done. My algorithm stops here. But if I choose something else, if I choose a new vertex, like if I choose my w not as 3 or not as 5, if I choose that either 2 or 4, then there is a problem. Why? The reason is w के जो neighbors हैं and the choice of s is different. So this n w intersection s is right now 2. If it is 3, I am done, but it is 2. So our objective is to increase nw intersection s. Now this algorithm gives you a procedure how to do this. So you have to increase. So 4 is such a neighbor in s. So sorry, 4 is in s, which is not a neighbor of w. And 1 is not in s, but it is a neighbor of w. So somehow you have to delete this and you have to add this. Now if you do that, what happens? If you add that and you delete that and you suppose, sorry, if you do this, its degree is 3, it has already degree 3, it has degree 2, it has degree 1. So you have to add this edge. Okay. So the challenge is how to choose this new edge. Which are the vertices? So one vertex definitely must be Z, which earlier was the neighbor of W. Now since it loses its 1 degree, so it has to create, we have to create some edge from here itself. Now why? The one point will be Z, one endpoint will be Z. What is the other endpoint of that edge? So the other endpoint will be that vertex Y, which is a neighbor of X but not a neighbor of Z. So this is one option. Another option could be no, this is the option, right? So since degree of X is greater than equal to dz and W is already a neighbor of Z but not X, there must be a vertex Y adjacent to X. Okay, so I will create an edge from here. If I create an edge here, its degree became from 3, it became 4. So I have to delete something from here. Any one edge I have to delete. So which edge I have to delete? So there must be a vertex Y adjacent to X, which is not adjacent to Z. Okay. So this is my Y. So my question is, can I choose this as my Y? Because X के neighbor ये है. I think, yeah, I also can do that also. So this is one option. Another option could be so So basically I get x, and I have 3 is a neighbor of 2. Basically what it tells, since dx greater than dz, then I can always find a y which is adjacent to x, y is adjacent to x, but not z. Okay, so I can choose this as my y also. Okay, now we delete wz and xy. I will delete this. Wz, and so this is my xy, and then I delete wz, and I will create like this. So in this case, this is my y. Okay. Now if I delete w, I get a guy 3 5. This is 3. Sorry. So now we delete wz and xy, and we add wx and yz. This is not my y. Okay. This will remain same. Okay. So if I choose this y, I can also do this. And now if I delete w, what will happen? So just I will copy this. At this stage, if I delete w, then I will get, again I will realize this. So this is one way, this is the second way. Other way. Other option. Basically choose 3. Choose vertex 3 as y. So algorithm stops here. So with this, we end today's lecture, and today I will mail you the slide up to this. Okay. Thank you.